few years ago, EVs looked like they were going to be the way of the future. They were fast, powerful cars that could also help save the planet. With CNBC even announcing EV euphoria is dead.
Liebherr contributes to the green mobility, which means CO2 reduction and improvement of air quality.
A combustion engine with zero emissions, a dual fuel system that could outperform electric motors in direct comparison, absurdly high power density, excellent efficiency, and 0 grams of carbon output. The key lies in using not one, but two fuels simultaneously that complement each other perfectly. Developed by Liebherr, a company traditionally known for heavy machinery, this innovation has industry experts talking about a new era for combustion engines. But why are two fuels so much better than regular diesel or gasoline? And more importantly, where will this technology actually make sense? The hidden challenge of heavy machinery electrification. When we talk about the energy transition, most conversations focus on electric cars, solar panels, and wind turbines. But there's a massive blind spot in this discussion that almost nobody addresses: construction machinery and industrial systems. We're talking about 40-ton excavators, dump trucks, and mining equipment that operate for hours on end under extreme conditions. These machines need enormous amounts of energy, often between 100 and 500 kilowatt hours per day, sometimes even more. To put that in perspective, 100 kilowatt hours of energy weighs about 8.5 kilograms in diesel fuel. The same energy stored in the most advanced lithium battery technology, NMC cells, weighs between 660 and 700 kilograms. That's not just a minor inconvenience. The payload capacity of these vehicles would be drastically reduced by gigantic battery systems. Imagine a dump truck that can only carry half its normal load because the rest of the weight is taken up by batteries. And then there's the charging problem. Even with fast charging, a 300 kilowatt-hour battery pack would need at least an hour to charge. Without fast charging infrastructure, you're looking at a full day. Construction sites would need 2 to 3 times longer to complete projects. That annoying construction zone on your commute? It wouldn't be there for 1 year anymore, but 2 or 3. Sure, you could theoretically develop an elaborate system with swappable battery packs and delivery infrastructure, but such solutions exist only in research papers and theoretical models right now. We need practical solutions for the coming years and decades, not concepts that might work in 2040. Why batteries struggle in construction and industry? The fundamental problem comes down to energy density and operational demands. Construction equipment operates in harsh environments, often far from electrical infrastructure. These machines work in remote mining sites, mountain road construction, and large-scale agricultural operations where grid access is limited or non-existent. Battery technology has improved dramatically for passenger vehicles, but the requirements for industrial machinery are entirely different. A Tesla can sit at a supercharger for 20 minutes during a road trip. A mining excavator that stops working for an hour represents massive financial losses. The economic equation simply doesn't work yet. Beyond the weight penalty, there's also the question of battery lifespan under heavy use. Construction equipment operates in dusty, vibrating, temperature-extreme conditions that accelerate battery degradation. Cold weather particularly affects battery performance, yet construction projects don't stop during winter. The replacement cost for industrial-scale battery systems would be astronomical. Additionally, the electrical infrastructure at construction sites would need complete overhauls. Most sites rely on temporary power setups that couldn't handle the load requirements for charging multiple heavy machines simultaneously. We're talking about needing megawatt-scale charging infrastructure at remote, temporary locations. The logistical challenges are immense. The ammonia solution and its problems. For years, industry experts have been discussing ammonia as a potential solution. Ammonia can be produced from hydrogen, and this conversion process is actually quite efficient compared to alternatives. Using ammonia is 2 to 3 times more efficient than using e-fuels or synthetic diesel. Unlike hydrogen, which needs to be compressed to 700 bar for acceptable energy density, ammonia becomes liquid at just 10 bar of pressure. That's roughly the pressure you create when pumping up a bicycle tire. This means ammonia doesn't require entirely new, expensive infrastructure. Existing tankers, pipelines, and transport vehicles can be used with relatively minor modifications. For industrial applications, this is huge. We're not talking about building million-euro hydrogen refueling stations for every construction site, but ammonia isn't the perfect solution it appears to be. The major problem is its high ignition temperature of about 650 degrees Celsius and its slow combustion rate. Ammonia burns approximately 10 times slower than conventional gasoline or diesel fuel. This leads to incomplete and uncontrolled combustion, which produces toxic ammonia exhaust gases. Pure ammonia engines have struggled with efficiency, reliability, and emissions. The slow flame propagation means the fuel often doesn't burn completely within the combustion cycle, wasting energy and creating pollution. Researchers have been trying to solve this problem for years without a breakthrough, until now. Liebherr's dual fuel innovation. Liebherr's solution is elegant in its simplicity. Combine ammonia with a stabilizing fuel. While you could mix ammonia with diesel, the real innovation comes from pairing it with small amounts of hydrogen. Hydrogen is highly flammable and ignites easily, and it can actually stabilize the flame formation of ammonia. The hydrogen acts as an ignition promoter, drastically reducing the rate of misfires and incomplete combustion. Liebherr developed this around a conventional-looking combustion engine, but the devil is in the details. The base design uses a standard 12-cylinder configuration, distributed across 2 cylinder banks, typically arranged at a 60 or 90-degree angle. However, inline configurations are also possible, which Liebherr uses for their pure hydrogen engines. The critical innovation lies in the injection technology. In February, Liebherr attracted significant attention with a new modular injection system that can handle both gases and liquid fuels. This gives access to a wide range of fuels: hydrogen, ammonia, methanol, and ethanol. With the latest announcement, it's clear this technology was designed specifically for the world's first dual-fuel ammonia-hydrogen engine. What makes this particularly practical is that the system could potentially be retrofitted to existing engines. This isn't just about building new machines, it's about upgrading the massive fleet of construction equipment already in operation. The economic implications are substantial because companies wouldn't need to completely replace their equipment fleets. How the technology actually works. The dual fuel system operates on a carefully orchestrated injection sequence. Ammonia serves as the primary fuel, providing the bulk of the energy. Hydrogen, despite being used in much smaller quantities, plays the crucial role of initiating and stabilizing combustion. The injection system must precisely control the timing and ratios of both fuels to optimize combustion efficiency. When the piston reaches the appropriate position in the compression stroke, a small amount of hydrogen is injected first. The hydrogen ignites easily due to the high compression temperatures, creating a stable ignition source. Immediately following, ammonia is injected into this hydrogen flame. The established combustion front from the hydrogen helps the ammonia burn more completely and uniformly. This solves the slow flame propagation problem that plagued pure ammonia engines. The modular injection technology is what makes this possible. Traditional fuel injectors are designed for specific fuel types with particular characteristics. Gaseous and liquid fuels have vastly different injection requirements in terms of pressure, spray patterns, and timing. Liebherr's system can adapt to different fuel properties, allowing the same basic engine architecture to run on various fuel combinations. This flexibility means manufacturers can adjust fuel ratios based on availability, cost, and specific application requirements. The engine management system constantly monitors combustion quality through sensors and adjusts injection parameters in real time to maintain optimal performance across varying load conditions. The nitrogen oxide problem. However, there's still a significant environmental challenge: nitrogen oxide emissions, commonly abbreviated as NOx. These are chemical compounds of nitrogen and oxygen that form during combustion, and they're extremely harmful to human health. Ammonia combustion is particularly prone to NOx formation because the fuel itself already contains nitrogen. This means SCR or NSCR, catalytic converters with ammonia reduction, are absolutely necessary for these engines. But catalysts alone aren't enough. Engineers must invest considerable time and effort into optimizing the combustion process itself to drastically reduce NOx formation from the start. Nobody wins if a new generation of engines produces zero CO2, but instead emits nitrogen oxides that directly harm the workers operating the machines. This is a critical point that shouldn't be glossed over in the excitement about carbon-free combustion. The health impacts of NOx include respiratory problems, reduced lung function, and increased susceptibility to respiratory infections. In enclosed or semi-enclosed work environments like tunnels or mines, NOx accumulation could create serious occupational health hazards. The industry must demonstrate that these emissions can be reduced to levels comparable to or better than current diesel engines, with modern emissions control systems before widespread adoption is viable. Where this engine makes sense and where it doesn't. This technology isn't going to replace electric motors everywhere, and that's an important distinction. It fills a specific niche where electric solutions currently fall short: heavy machinery operating for extended periods in remote locations. Mining operations, large-scale construction projects, agricultural equipment, and potentially marine applications are the prime candidates. These are applications where the energy density advantage of liquid fuels remains crucial and where charging infrastructure is impractical. However, for applications where electric solutions work well today, this technology offers no advantage. Light construction equipment, urban delivery vehicles, and passenger cars are already being successfully electrified. The dual-fuel ammonia-hydrogen approach adds complexity and requires new fuel supply chains that make no sense when simpler electric solutions exist. The real question is how long this niche will remain relevant. Battery technology continues advancing rapidly. What seems impossible today might become routine in 5 years. The trucking industry is already seeing this shift. New battery technologies are emerging that challenge the assumption that long-haul heavy vehicles must use combustion engines. The window of opportunity for dual-fuel combustion engines might be shorter than manufacturers expect, or it might last for decades in truly demanding applications where energy density remains paramount. The shifting battlefield between combustion and electric. The reality nobody wants to hear is that the domain where combustion engines dominate shrinks with each passing year. New battery technologies can completely overturn these predictions overnight. This recently happened in the trucking sector. CATL, the Chinese battery manufacturer, released a battery system for electric trucks that outperforms combustion engines both economically and in terms of performance. These latest batteries from China are so advanced that other countries will struggle to catch up. Double the range and charging to 70% in just 15 minutes. The playing field is shifting faster than many traditional manufacturers anticipated. Liebherr's dual-fuel engine represents genuine innovation for a real problem, but it exists in a rapidly evolving competitive landscape where the advantages of combustion, even carbon-free combustion, are steadily diminishing. The technology might serve as a crucial bridge solution for the next decade or two, particularly in the most demanding industrial applications. What we're witnessing isn't the replacement of electric motors by a new combustion technology, it's the opposite. Combustion engines are being pushed into an ever narrower range of specialized applications where they still hold advantages. The dual-fuel ammonia-hydrogen engine is a sophisticated solution for that shrinking niche. Similar innovations will be necessary for aviation and shipping, where energy density requirements remain extreme. But the trajectory is clear. The question isn't whether electric will eventually dominate, but how quickly that transition happens and what role technologies like this will play in the meantime.